post the video?
They're on my YouTube channel, so it's linked from Brightspace, but you can also always just like click on the channel if I haven't added it to the playlist yet.
Okay.
If you have trouble finding that link on Brightspace, just shoot me an email and I can send it out directly. Or, you know, I'll just send out a group email after class. It's easier. Okay. So today we're going to start out with a couple of questions about the resting membrane potential, which is what we left off with on Monday. And then we'll move into talking about action potential. It's the main thing we're trying to understand. Now that we're into thinking about neurons, you will be expected to know approximately where the equilibrium potential for potassium and sodium are, which slide's not listed yet. Take another couple seconds. And then I'll take a look. This is thinking maybe about that imaginary just potassium cell that we went over. Okay, so we're kind of on the right track. So when we're talking, right, we have our cell. We know it's quite permeable to potassium, only a little permeable to sodium. So we're going to have some potassium channels. And further, you know, potassium is positive, and we know that its equilibrium potential, so EK, is very negative. So EK is in the range of -94 millivolts. Further, we know that the resting membrane potential is -70 in a neuron. So in order to get closer to its equilibrium potential, potassium is going to go out. And we do have channels that allow this to happen. This is a dynamic process. That's why we had that sodium potassium pump maintaining kind of our chemical gradients. So when the positive charges move out of the cell, that would make the cell more negative. So we should have picked this answer E. The force is out, which would make the membrane potential more negative. Any questions about that? So let's try another one. Now we're gonna think a little bit about sodium. We talked about what both sodium and potassium are doing to maintain that resting membrane potential. Let's see, which of these things we can remember. Okay, take another couple seconds to pick an answer. Okay, great. Most of you who answered got this right. So when we have our cell, we know that it is permeable to both sodium and potassium, but it is way more permeable to potassium, which I've drawn a circle, than to sodium. So that makes this one and this one true, D and B, which leads to this answer A. Because we don't have too many channels, while we are quite far away from the sodium equilibrium potential, which is like positive 60, even though we're quite far away and sodium really wants to get into that cell, it can't get through, so it moves quite slowly. And it is true that there's a strong inwardly directed electrochemical driving force, which is going to have a big impact on what happens during our action potentials. So we can tell that because we're at negative 70. So we're way far away from positive 60. And we're much closer to the potassium equilibrium potential of negative 94. Finally, this is a little bit of a prediction question, or maybe a sense of how far you've looked ahead. You could potentially get it from some of the words I've been deliberately using about what's going on here with sodium and potassium. So we know that there are channels allowing sodium and potassium to move. And what types do you think we've been talking about so far as we've been talking about the resting membrane potential? We'll see all of these as we move forward today. Quick answers. Another couple seconds. Let me click through. Great. Yeah, we've been talking about sodium and potassium leaking in and out of the cell, respectively. These channels don't have a gate, so these ions can move through all the time. They're responsible for what the cell is doing at rest. But as we move forward, we'll see that signals are going to come in, open these gated channels. So signals are usually going to affect these ligand-gated channels. And the action potential will have to do with triggering of a bunch of voltage-gated channels that can be triggered by changes to the membrane potential. As we left off, we're talking about graded potentials. So here we see on the bottom someone else's drawing of a neuron, right? So the axon is over here on the right. We have this area of the axon hillock, which is this very first part, branching off the body of the cell. And their dendrite here just little spikes. So what's going to happen when a stimulus comes in to our neuron, and a stimulus, depending on what we're talking about, could be something like you touch something, could be a temperature, or it could be another neuron firing and sending a neurotransmitter. So stimulus is just something that happens near this cell. When a stimulus comes in, the way the neuron is going to respond is by creating a small change in the membrane potential. So whatever that stimulus is, it's going to change our voltage across the cell. So the easiest example to think about here really is the example of another neuron signaling to it. So if we have a neurotransmitter come in, right, like maybe we have some serotonin or something, what it's going to do is bind to a channel, basically. So this would be talking about like our ligand-gated channels from that previous question. So we'd have a neurotransmitter bind on and open a channel. That's kind of conceptually what's happening to create this change in the membrane potential. We're not really there yet, but I think it's helpful to kind of know that. So the graded potential refers not to the stimulus itself, but to the small change in charge. It's very local, so it's right near the area of the neuron where that stimulus came in, where that channel opened and closed. So we call them graded because they're not going to change the whole cell, the whole membrane all at once. And we can have big changes and we can have little changes. So that's what the graded means. It comes from like the word degree. So once we have this small change here, this graded potential coming in, that change in charge, which is really just the concentration of ions, is going to spread out. But what you'll notice about these arrows, right, they're getting smaller as we get farther away from our stimulus. So you can kind of imagine that, like, say you have a handful of marbles, right, and you throw out. Right, when they hit the ground, they're all together, so there are ions in this example. But then they start rolling and they spread out. So, you know, they're getting weaker, they're rolling slower as we get farther away from that point of impact. So that's what's happening with these ions. And that's kind of what's happening with this effect on the local membrane potential as we move away from that stimulus. So we refer to that property as decremental, coming from the word decay, right? Decay, decrease, right? That's the root. So they're decremental, meaning they get weaker as we get farther away from that. So that's specifically true of graded potential. If we were to look at them on a graph, we can see what's happening with this graded potential, right? So we're starting at our initial time point here, right? We're moving along. So at X here, we'd have some stimulus come in, having some effect on channels in the membrane, and therefore having an effect on charge, an effect on membrane potential. So we have a little blip that then decreases and fades away as time goes on. It dissipates, it decreases. If we had a stronger stimulus at a future time point, we would have a stronger graded potential. So you can see that the levels are a little different. The second one is higher. And part of the reason we're specifying this is that graded potentials can be weaker or stronger. But when we talk about action potentials, every action potential is the same. So this is specific only to these graded potentials. And here at the bottom, what this figure is showing us is another way of thinking about this decay as we spread across space. So we're taking a look here. I'll clear all my drawings. Our first point is looking at what it would look like if we recorded the charge as the stimulus. Right, so that's here. And then the second point is looking at what would happen if we measured at the axon hillock. So we can see that this is lower, right? So we could draw a line across. And we care about this because as we start to talk about action potentials, we're really going to be talking about what affects the axon hillock, because this is where the start of our action potential. So now we will draw another little cell. And go ahead and draw along with me. And this time, maybe let's give them an axon hillock and the beginning of an axon, just so we know that exists. In this first example, let's imagine we had a ligand-gated sodium channel. We have a signal come in that opens this channel. I'm going to erase. Nope. I was trying to erase the center of this. I'll just have to imagine it. I was going to erase this here, but let's say this opens now, right? So what does this do to the permeability of sodium here in this area? Increase or decrease? More channels, increases. Okay. So what's going to happen to sodium when we have this stimulus open this channel, probably by binding on? It's going to go in or out?
Are we expecting it to be on the membrane?
Yep. Yep. Basically, for our purposes, sodium is pretty much always going to want to go into the valve. Okay, so sodium's going to go in, which means we're going to have a little bit more positive charge here. So maybe we go in this local area from, I don't know, -70 to now we're at -65 or something. As the sodium ions spread out, maybe farther away, say at our axon hillock, we're decaying. So maybe here we're only at -69, right? So we still have an effect depending how far away we are, but it's not as big as at that point of contact. So on the potassium side, same kind of thing could happen. All right, so let's say we have a stimulus come in and it opens a potassium channel. Which direction is the potassium going? We just talked about this in our first multiple choice question. Perfect. potassium is going out. So what is that doing to our membrane potential? More negative or less negative? Yeah, exactly. We're dropping down closer to that negative 94. So now we're going to be at like negative 75. So maybe if we measured at our axon hillock, we'd be at like negative 72. So as we talk about these moving forward, we would refer to the sodium one where we're getting more positive. We'd refer to that as depolarization. We would refer to what's going on with the potassium as hyperpolarization. And these are words that we'll use for graded potentials, but they're words we'll use in general for changes to the membrane potential as well.
So when you talk about the negative 75 and the negative 72, we're talking about the membrane potential.
Changes to it right there.
They can change part of the neuron.
Yeah, we've been talking about it thus far as like the whole cell, but because the neuron is like spread out, like it does happen at an actual point.
Okay, and then depolarization, that's when the cells become more positive.
Yeah. So these graded potentials, these responsive locally to stimuli, the reason we care about them is because we're trying to figure out whether we want this neuron to signal, whether we want to go tell other nerves in our chain of nerves to fire and to do something. So in order to fire off our neuron, in order to fire off an action potential, which would be like the next step if we get a bunch of graded potentials get really big. If we hit a threshold of negative 55 millivolts, then we will fire off an action potential. So in either of those two examples we just drew with little graded potentials, are we going to fire off an action potential? No. So a cell can receive a signal and not respond to it, not signal to the next cell. We have to reach the threshold for us to send something off down our axon and eventually release neurotransmitters. So graded potential doesn't always cause an action potential. We might also want to, or a common way to refer to neurons in general and their effects, and therefore also to stimuli and their effects, using these terms excitatory and inhibitory. So these do pretty much correspond to depolarization and hyperpolarization. So excitatory stimuli make us more positive, inhibitory stimuli make us more negative. But the reason we're using these words, right, is that what we're really focusing on when we use these terms is we're saying, are we getting closer to this threshold? And if yes, our neuron is going to fire, so it's excited, right, doing something. If we have a hyperpolarization event, right, so like our example with the potassium leaking out, making the cell more negative, it's going to be harder to get to that threshold, right? Like if we drop from negative 70 to negative 80, right, we're going to need a lot more excitatory events to come in and override that. So we'd say it's inhibitory because it's kind of preventing our neuron from signaling. And when we eventually get to synapses and neurotransmitters, we'll see that some neurotransmitters, some neurons affect future nerves in our kind of like chain of nerves in excitatory or inhibitory ways. Like both of these are useful for your body depending on what you're trying to do. Negative 55. Yep. Approximately. this system wouldn't work very well if we always only had a single graded potential and we left enough time for it to decay, right? Like if we always had to just open every channel one by one, that wouldn't do much for us. It would really be hard to get to our threshold. We'd have to have a really big signal coming in. So what happens with graded potentials is that we can add them together. And there are two ways in which they can get added together. They can get added together because they're happening really fast, one after the other. And so they're kind of snowballing. One doesn't have time enough to decay and before the next one hits. And the other way we can have this happen is if we have signals coming into multiple points on our cell. If they come into multiple points, basically in the middle, where those like arrows of spreading out overlap each other, at those points, we would add them together. And so if they're adding together as they reach the axon hillock, we'd add them together and they get closer to the threshold. So in temporal summation, we're thinking about them hitting basically the same spot. So you'd be getting like the same stimulus over and over again. Like your body's telling you, this thing is still happening, come on. Spatial summation, you'd have essentially different stimuli coming into different parts of the cell, but your neuron can kind of sum these things together and still want to have a reaction. Since we're separating them out this way, we're going to think about the spatial summation ones as overlapping in time. So we can shorthand think about them like happening at the same time. Yeah.
Are they both added together or
Yeah, these are both ways that can add together. So what we see happening here in the top one, top image here, would be an example of our temporal summation. Actually, both of these graphs are going to be examples of temporal summation. I'll just write that at the top. So what we see happening here basically is we have something firing off a little graded potential here. Maybe we have some sodium come in. It faded away. Then we have another signal come in. But before it fades away, we have another signal come in, a big one, gets us to positive 55. And then we see this curve, which really you will come to know and love. That's our action potential. However, not all our stimuli are excitatory, right? That was 3 excitatory stimuli in a row because they depolarize. You have these little uplifts. So we should note that if you have an excitatory stimulus and then an inhibitory one, you could still add them together, but if you add a positive and a negative, you're not going to get any closer to the threshold. You're just going to kind of even out to 0. So if we're thinking temporal summation at T1, we'd have like one signal come in. And let's say this takes us to, doing math on the fly, this takes us to negative 60. At T2, we have some decay of that signal. So maybe we start to go back down to negative 65. But now we're starting at a little higher point. Oops, I should have erased the stimulus. Sorry, guys. So this is kind of a resting point between. And then at T3, we have another signal come in. This is a really big one. Gets us to negative 55 because it didn't have as far to go. So then we would fire off an action potential. So that's kind of what that would look like versus in spatial summation, what we're talking about, like this actually looks slightly more neuronal here. We're talking about two signals coming in. Let's say each of them at this point raise the local membrane potential by 30, which means over here maybe we're at plus 20, so that would be 50 total, sorry, negative 50. So here, another 10, but the same thing would be happening for this other one. So then we could add these two together. So at this point, what is negative 70 plus 20? Negative 50. Great, it's an example which would fire stuff off. The negative 50 being higher than negative 55 would fire off an action potential.
Would the only fire off if it hits the threshold, like the action helic?
So the action helic. Pretty much. So the action helic has a lot more voltage gated channels, which we'll talk about. So it's the most responsive to changes in charge.
Right, but if you get the negative 55 membrane potential just in the rest of the cell, it'll still trigger off the threshold.
I think it would depend on how many voltage gated channels we have there. So
But we're primarily talking about.
we're thinking about the action helic for our purposes, yeah.
What were the
Ooh, that's a good question. So I think a spatial summation, if we were looking at the overall charge change here, would probably just look like a big jump up to negative 55 or above. But if you wanted to indicate that it was spatial summation, you might draw two arrows, right, saying it's multiple, or you might draw multiple lines, right, like saying that this is one of our graded potentials, and this is our other graded potential, and then they're adding together. Further questions about temporal and spatial summation? Because I know that this can be kind of tricky to wrap your mind around. We'll do more practice questions on this next time. Overall, as we're thinking about these graded potentials and just thinking about the properties of a graded potential, why do you think they can't communicate really far away? Like, what would happen if instead of just getting this signal to the axon helic, why can't you get a graded potential going all the way to the end of the axon, to the axon terminal? Exactly, yeah. As we move farther away, these graded potentials are decremental. So they decay too quickly, they dissipate, they fade as they get really far away. And that's why we need the action potential. The action potential is not going to decay. This is not an exact picture of our action potential, but it's labeling how we would talk about the directions here. So we've talked about how going up is depolarization and down is hyperpolarization. And we're always comparing to our resting membrane potential. And just so that we remember it exists, our threshold might be like here. The one other word we want to kind of tack on to our knowledge here is this word repolarization. So this is kind of like the hyperpolarization. We're going down. The only difference here is that we're being a little more specific. So repolarization is going to be going back down towards the resting membrane potential after we have had a depolarization. So our hyperpolarization and our repolarization might have like similar movements of ions because they're both moving down. But we're basically specifying kind of if we're going back down to the resting potential or we're going below it. But we'll also see that in terms of the action potential, the repolarization is really just erasing this depolarization. So they're kind of linked to each other. So here is a cheat sheet on different types of ion channels and where they are and how they work. Because it's a wall of text, I'm going to draw alongside it just because. So we have our neuron. These spikes are my dendrites. The circle is the soma. As we taper off, we're on the axon hillock. And then we have our axon, and it's going to split into some axon terminals. So our leak channels are those ones that were always open and are maintaining our resting membrane potential. So we'd have them everywhere because they're keeping the neuron at that -70. We're basically going to want all parts of the neuron to at rest be at -70. It's not like the body of the cell, the round part, is at a different resting membrane potential than the terminals. Think of the whole thing as -70. Next, we'll have the ligand-gated channels, which basically work by having a closed state. And then in order to open the channels, we have our molecule bind onto them. That's the ligand part. So we can think of the thing that's binding on as like a neurotransmitter, maybe some type of hormone, something like that. And this is really how we're receiving stimuli. So this is how we're receiving signals. So we're going to see them in the parts of the neuron whose job it is to receive signals and figure out how to add together these graded potentials. So we're going to see our ligand-gated channels in our dendrites. And we'll see some on the body of the cell, the soma. We're not going to see them out in the axon or in the axon terminals, because those are basically our signaling highways. We don't want random little signals coming in and messing with our action potential. So we're not going to have these ligand-gated channels. They would mess us up. They would have potentially their own effects on charge. Brings us to our voltage-gated channels. Now. Okay. So we will be taking a super close look at voltage-gated channels and what different ones look like. For now, I'm just going to kind of have them being an H. So our voltage-gated channels are going to be closed at the membrane potential at -70. But these are the ones that are going to change when the membrane potential changes. The first ones that are going to change are responding to that threshold at -55. So we're going to see them throughout, but they're going to really be concentrated in the axon hillock, which is why we care about the summation at the axon hillock. So there might be like one over here or over here or something, but they're going to be here. And they are going to be responsible for propagating or sending our action potential. So we're also going to see them in the axon itself. And there might be a couple here as well. Finally, we have a calcium channel. So our calcium channels are like another type of a voltage-gated channel. We'll have voltage-gated channels that are specific to sodium, that are specific to potassium, and that are specific to calcium, and they're all going to work in slightly different ways and look a little different. But the calcium channels are what's going to release our neurotransmitter at the end. So we're going to see them in the axon terminal because they have a special role. So calcium is not going to play a role in our action potential itself, but it is going to trigger the release of our neurotransmitters at the end of this process. So questions so far? This brings us to what exactly an ion gate is, or why it would change, why we care about it. So our ions have to move through a channel to get into our neuron, because otherwise they're just going to bounce off that non-polar region of our cell membrane, right? They can't get through our phospholipid. So we have the leak channel that we've been thinking about as maintaining our resting membrane potential, keeping us at -70. So those aren't gated. They really can't open or shut. What we care about for our leak channels is just how many of them there are. Specifically, that we have lots of them for potassium. And when we talk about voltage-gated channels, we're going to be seeing that they open and close. So they're going to have like a little door in the center. So they're going to have their normal channel walls. So when they're open, they might look something like our normal channel. But we're going to see that when they're closed, they have a wall here. And our sodium ones are actually going to have two potential walls. We'll see they have two gates on there. We're going to take a look first specifically at the voltage-gated sodium channels, because this is really the main thing we have for sodium. That membrane isn't really significantly permeable to sodium at rest. We don't have hardly any sodium leak channels, which is why we're really near our potassium equilibrium potential. However, sodium is huge for our action potential. I would consider sodium like the most important thing for how our action potential. What happens is when we reach our threshold of -55 millivolts, we're opening sodium. Sorry, opening these voltage-gated sodium channels. So we want to think now about our electrochemical driving force on sodium. Was it like just a little bit, or was it strong? Did we have like a weak or strong force? Yeah, we have a really strong force. The only reason sodium hasn't been traveling into the cell is because it couldn't get in. So when we hit -55 millivolts, we'll see that the first part of our action potential is going to be this huge depolarization, this big rush up, this big peak. Sorry, yellow doesn't show up very well, does it? Okay. This big peak, so from -70 to like +30. Okay. And the reason this is happening is these voltage-gated channels. So when we had gated channels that opened to our threshold of -55 millivolts, all these channels start to open, and this basically snowballs. As you start to open more sodium channels, this is going to make neighboring parts of the cell rise to threshold, which is going to open more sodium channels, which means their neighbors are also rising to threshold, which means more and more sodium channels are opening. So this is an example of positive feedback in the body. If we look at the structure here, we'll see that there are two gates on the sodium channel. So there's an activation gate and an inactivation gate. And this first image is showing us the situation of our voltage-gated sodium channels at rest. So what we should be noting is that the activation gate is the one that's blocking sodium from entering the cell when we're at rest. Our inactivation gate is open at this resting state. So that -55 is the trigger for this internal activation gate to open. So that's our time point 2. So here, sometime between 1 and 2, we hit -55. We set off this wave of depolarization, opening that gate. But our sodium channel isn't done yet. It doesn't stay open forever. And our neuron is never going to get all the way up to +60. So there's a time delay on the second kind of phase of our voltage-gated sodium channel. And that has to do with our inactivation gate. So we turn off these sodium channels by popping that inactivation gate and closing it off. Our activation gate here is still open for a little while this inactivation gate is closed. So this is stopping sodium from coming through. So that's at 10.3. And then eventually we get back to our resting state. So the activation gate would close and the inactivation gate would open. And at that point, we'd come back to our resting membrane potential. So our key points here: voltage-gated sodium channels open at -55, and they close through the inactivation gate, so they get deactivated once the cell hits 30 millivolts. So these are two time points, or sorry, two membrane potentials that we're going to see on basically all of our pictures of the action potential on all of our graphs, because they're really key, because they're changing what sodium can do, which means that these are going to have major effects on what's happening to the charge in our graph. So we will pick up here next time. And next time we'll talk a bit about potassium. Yeah, for sure. What do you want to look at? This? Okay.
I didn't even get. Wait, which one?
This one. We'll be talking a ton more about these different types of voltage-gated channels, but we're like kind of done thinking about the leads and losses. Try to mention them some more so you guys don't forget about them in the next couple of weeks, but when we start to talk about synapses, they'll be important. It'll be a while before we get there. So you don't have to learn about them now, but we'll go through in detail the, like, I don't remember how many, like 12 steps of firing off a neurotransmitter in the axon. So you will see more descriptions of the calcium channels. Oh, is it? Good.
What I figured out is that No, I'm taking my organic chemistry and that stuff right now too.
Mm-hmm.
So for that first part with the lipids and
Uh-huh.
everything, it was a little boring because now I'm getting into it in chem. So I'm like, oh, this would have been nice to know before I took this class.
To change them, yeah. Did they not get into that much in Gen Chem? Did you take Gen Chem before?
Yeah, I took that.
Yeah.
There was
Did they not talk about that?
No, there was no organic chem. 'Cause I took it out of
That's
there.
good to know. Oh, okay.
Yeah, so
Okay.
that's why I'm taking the nursing chem.
Right.
Oh, so much.
Yeah, we try to like pair those together like before this.
Yeah.
With the idea that this is like the third time you've seen it, because it's also in the bio the cell class that some people take before. Have you taken that? Are you nursing?
Yeah, I took biology.
Okay.
And there was some of it, I took just general biology, and then I took microbiology over the summer.
Okay, so
And-
those kind of
But
transferred in.
with microbiology, all it was, it's just, we were doing, the little petri dishes. That's all we did, was like growing bacteria. We never talked about these, nothing.
Huh.
Yeah, so I think
Weird.
that's why I was a little confused, but now
Okay.
I'm getting it.
Okay,
But-
good.
Yeah,
Yeah, it's unfortunate. That first section is really based on like our curriculum, it should be review, but if you were transferring in other credits, I can see why that would like
And now-
really put you at a disadvantage if I'm like, okay, so remember last year when.
Yeah, right. And now I'm getting like the CDF and all that. That makes so much more sense now that we're in this chapter than it did before for some reason.
Having a reason to think about it is helpful.
Because before I'm like, what is the point of this? I don't understand. And now understanding this, now I'm like, oh yeah,
Yeah.
the positive is gonna flow in when there's negative membrane potential. I'm like, yeah. it's just
I love
like,
that. I
makes
love
sense.
that. I love hearing that.
Yeah. I'm like, I
That's
have a
good
reason
news.
to know it.
Yeah.
Besides just memorizing from.
Yep, there's a reason we talked about it. Yeah, you too.